Hello, everyone, and welcome back. In the previous lectures, we discussed why we build models in electronics and the idea of empirical modeling, and finally, what thermal equilibrium meant. So, in now we are ready to answer one of the most fundamental questions in semiconductor physics, right? So, why is silicon special? Like everything we hear regarding chips and electronics, they say it's made of silicon, but why? Silicon sometimes behaves as an insulator. Why does it do that? And under right conditions, suddenly it starts conducting electricity. So, to answer that, we need to zoom in all the way down to the atomic level. So, in today's lecture, we'll understand how silicon atoms arrange themselves into a crystal, how the said atoms share electrons through covalent bonds, then what happens at absolute zero, and why electrons need energy to conduct. And finally, we will develop the idea of energy bands, which is one of the most important concepts in semiconductor electronics. So, let us begin with the silicon atom itself. Silicon is element 14 in the periodic table. Its configuration is 284, where these four electrons are the outer valence electrons, and these are the most important part for us. They participate in bonding. So now imagine we have four hands. Quite a gory example, but just stay with me, right? So each hand wants to hold another person's hand. A silicon atom is exactly like that. It has four hands, that is the four valence electrons, and naturally wants to form four bonds with neighboring silicon atoms. This is a simple fact that is responsible for the entire crystal structure of silicon. So now imagine we keep bringing silicon atoms together. Each atom wants four neighbors, right? So eventually, every silicon atom finds exactly four neighboring atoms and shares one electron with each of them. So these are called covalent bonds. So we can think of an example. Say there are four friends sitting around a round table, right? And each of uh, the student want instead of buying their own book, each pair shares a book, right? And both people can use it. So this and no one completely owns the book. So that's exactly what happens with a covalent bond. The bonding electrons are shared between neighboring atoms. So now another question arises. How are these four neighbors arranged? They are not arranged in a square, that is, they are not on a flat plane. Instead, they occupy the corners of a tetrahedron. A tetrahedron is a pyramid with four triangular faces. So if you place a silicon atom at the center, its four nearest neighbors sit at the corners of the tetrahedron. This arrangement minimizes the energy of the crystal and makes the crystal structure extremely stable. When tetrahedron arrangement repeats itself millions and millions of times, we obtain a single crystal of silicon. This crystal is called the diamond lattice. And here there's something interesting from a crystallography point of view. The silicon crystal can actually be viewed as two centered lattices interwoven together. One lattice is shifted by one quarter of the cube's body diagonal relative to the other. Now, I get this sounds complicated, and honestly, for most semiconductor device analysis, we do not need to visualize every atom in the three dimensions. The important takeaway is simply that every silicon atom has exactly four nearest neighbors connected through covalent bonding, and everything else follows from that, okay? So, because drawing the three-dimensional crystal quickly becomes really messy, we often use a simplified two-dimensional picture. So that's shown here. So in this diagram, every circle represents the nucleus, and uh, the nucleus and plus the tightly bound inner electrons, right? So the 2,8 that we saw earlier. So together, these are called the iron core. The lines connecting the neighboring atoms represent the shared bonding electrons. So, although the picture ignores the actual three-dimensional geometry, it perfectly captures what we care about, right? Where the electrons are. So, we saw this in the first lecture, right? Modeling a model is said to be successful as long as it serves our purpose and it's accurate within the framework that we want to observe, right? So sometimes simple models are more useful than perfect models. So that's something we already discussed in our lecture on modeling. So let's perform a thought experiment, okay? So suppose we cool the silicon crystal all the way down to absolute zero or 0 Kelvin. At this temperature, the crystal contains no thermal energy and the electrons remain in covalent bonds. And every electron is in its lowest possible energy state. This means that the inner electrons stay close to the nucleus, outer electrons remain inside covalent bonds. There are no free electrons moving through the crystal, right? So no mobile charges, no electrical conduction. In other words, so basically silicon behaves like an insulator at 0 Kelvin. This surprises many of us because silicon is famous for being a semiconductor. But remember, at absolute zero, it doesn't conduct at all. So now let's slowly warm up the crystal, right? So as the temperature increases, the atoms begin vibrating. These vibrating atoms continuously collide with the electrons, and every collision exchanges energy. So imagine children sitting inside a classroom, right? They're all seated quietly. Now imagine the teacher starts playing some energetic music. The students begin moving around, and some are still sitting, some are standing. We become energetic enough to like run around the classroom, right? So temperature works in a similar way. The higher the temperature, the more energy the particles exchange. And average thermal energy is uh, given the symbol kT, where K is the Boltzmann's constant, and at room temperature, this become approximately 0.025 electron volt. And this number is extremely important because it's recurring in a lot of the calculations we would be doing, and we encounter it repeatedly through semiconductor physics, so it's worth remembering. Now comes one of the most important idea in electronics. So instead of thinking that is our energy level. So instead of thinking about individual atomic energy levels, we think in terms of energy bands, right? So say we imagine, say just think of a multi-story building. The lower floors are completely occupied. The upper floors are empty, and between the two groups of floors there's an inaccessible gap. So electrons behave similarly. The lower occupied energy level forms the valence band, and the higher energy levels available for free electrons form the conduction band, and separating them is an energy gap called the valence band. Sorry, I meant like this my bad, the separating energy gap is called the band gap. So the valence band, Uh, this contains the bonding electrons. It is normally filled electrons that participate in covalent bonds, and the electrons are not free to move. So then the conduction band is the higher energy band. Electrons are free to move, and it is responsible for electrical conduction. It is empty at absolute zero. Current is carried by electrons in the conduction band. Now, the third part, which is the band gap, this is in between the valence and conduction band. So, for silicon, the band gap is 1.12 electron volt. This is the energy that must be supplied to free an electron from the covalent bond. The electron that's residing here can go to here if we provide a minimum of 1.12 electron volt. So notice something interesting, right? At room temperature, thermal energy is only 0.025 electron volt, but the silicon band gap is 1.12 electron volt. So this means that the average electron, right, does not have enough energy to jump from the conduction band into the valence band. So imagine, say, there's a wall about 1 meter high. Most people walking normally wouldn't accidentally cross it, but every now and then someone may run and jump over it. So, similarly, electrons remain in the valence band while a very, very small fraction acquire enough energy through collisions to cross the band gap. And once an electron reaches the conduction band, it is no longer tied to a particular bond. It is now free to move throughout the crystal. And once charges can move, what happens? Current flows. This is a fundamental reason that semiconductors conduct electricity. And that's why we're interested in them, right? Um, let's connect what we've learned so far. So, silicon atoms have four valence electrons. They share these electrons with the four neighboring atoms. This forms a stable diamond crystal. At absolute zero, all electrons remain inside covalent bonds. No free electrons exist, and the crystal behaves like an insulator. Now, when we increase temperature, some electrons gain enough energy and they jump across the 1.12 electron volt band gap. These electrons enter the conduction band, and now electrical conduction becomes possible. So let's just summarize what we have done in today's lecture. Silicon has four valence electrons. Each atom forms four covalent bonds. The silicon structure is called the diamond lattice. At absolute zero, no electrons are free to move. Thermal energy allows a small fraction of electrons to escape their bond, and these two are separated by a band gap of 1.12 electron volt in silicon, right? This is different for different materials. And electrons in the conduction band are responsible for electrical conduction. In today's lecture, we learned the atomic structure of silicon naturally leads to the concepts of energy bands. But we have only told half the story. When an electron leaves a covalent bond, it simply doesn't disappear from the valence band, right? It leaves behind something equally important. The missing electron behaves like a positively charged particle called hole. So, in the following lectures, we'll definitely understand what holes really are, why they behave like positive charge carriers, and how both electrons and holes work together to make semiconductor devices work. So, that's it for today's lecture. I'll see you in the next lecture.